Thank you very much for the organizer for the invitation. It's a great honor to talk here in a conference dedicated to Nigel Hitchin. The topic will be G2 structure, and I will not put the picture of the paper by Nigel, but the influence paper related to G2 and the relation with dimension state is a paper stable form and special magic. That paper was published in the proceeding of the conference dedicated to the memory of the Alfred Ray, which gave a great contribution to G2, organized by Marisa Fernandez, which is another person that will be very important for G2 geometry. So let's start. And the first thing, let's start with, I will give some background about G2 geometry, known example, some construction that I obtained in that direction, and also some general results related to Laplacian flow, the geometric flow, which involves a special type of G2 structure, called closed G2 structure. And in particular, I will say some results about exact G2 structure. So the idea is to present an overview and also to present an open problem related to that. So let's start. What is G2? We can see in two ways. That's the automorphic group of the Tonya. Here we see the Tonya as the sum of two copies of the quaternion and as a stabilizer of a stable free form. Here for stable, I mean that the free form belongs to the open orbit with respect to the general linear group. We will see a way how to get this free form. That way is in terms of the vector cross product. Let's see this remark. So if you take the multiplication of quaternions, this can be described internally in terms of the linear product and the vector cross product, or free, that you identify with the imaginary quaternion. And you can see from here the expression PQ. So you just write the scalar part in P and the part on free, and you can see that it involves essentially the scalar product and the cross product. Alfred Ray defined in a similar way, generalize that vector cross product on R7 that you identify in the imaginary part of the tonions, and you can see that the way you just take X and Y, and you take the imaginary part of the product. And one can define it naturally, the free form, associated free form, just using the cross product, vector cross product, and the scalar product. If you write down in the standard deity of 7, you can write down the form, the free form, in that way, where P1 to 7 is for instance the wedge product of P1, P2, P10. And the important thing here that if one takes the action of the linear group, the orbit under the action of the linear group is of P4, and P0 is that P4, and G2 is just the subwife of that form. In particular, we have the G2 is compact simply, it's a group of SO7, but let's go to geometry. So the dimension where we are will be 7 dimensions, and we say that the G2 structure on 7 manifold is just given by a free form such that in every point you can transform by a linear isomorphism to the G0 that they are before. So we have reduction of the frame bundle from the linear group to G2. And so point by point, you have that before, which is the freedom fraction. The first thing here, the existence of such G2 structure, which are topological fraction. In fact, this is the first result by Alfred Ray that shows that the 7 manifold has G2 structure, even though it and is orientable and peak. So even on if the first and the second, so we one of the two classes tension, one thing that is important with geometry is special with respect to other geometry. The free form is also determined the Riemannian geometry associated, because in fact, phi is not linear. That means if you take the contraction of phi by f, you wedge the two forms and then to tell with phi, this is not linear for any non-zero vector phi. And then you have a metric and a volume form. So automatically, a free forming also to have the Riemannian metric. And the condition for the free form to be parallel with respect to the Chita, associated with such metric, is exactly equivalent to the closure of the free form and of the start of the free form, so the four form, and so the one stop of phi, and the condition to allow me of the metric to be established. So we're talking about the true structure which is parallel when one of the three conditions, which are equivalent, is satisfied. And one can see also the same term like torsion free, because the combined derivative with respect to the Chita connection of the free form is the torsion, the intrinsic torsion of the Chita. G2 is one of the possible autonomy group for the reducible non-symmetric Riemannian manifold, we know about the shape theorem. And one thing that's important to remark that the condition for the closure of phi is linear, but if you look at the condition for the co-closure, okay, this is non-linear condition for the parallel with respect to phi. And another important thing is that the metric associated to parallel to structure in the H flat. That's what's shown by the map. Okay, let's see example of metric with polar. The first example was constructed by Brian, then on small ball in R7 using a stereo differential system. Later on, Brian and Fino construct the first complete homogeneity one example. In fact, this is the first link with dimension 6 due to Nigel, because you can, in some way, construct. In general case, you have incomplete metric, but the metric will holonomy contain G2 by evolving what is called an isofree structure in dimension 6. With the isofree structure, you have a pair of a 2-4, which is non-linear, and 3-4. So you can think that this 3-4 is inducing a complete structure, and essentially the 3-4, the real 3-4, is the real part of the 3-0-4. And then you have these two conditions: the rho with 3-4 is closed, and the wedge of omega 2 times is also closed. That in literature is called R flat, because you have a condition half of the intrinsic torsion vanishing, essentially. This is a nice tool that we use in many cases. The first thing we use is construction by Lu of the Gibbon called Select, where they construct metric with holonomy 2, whose dishonesty is an important group. And the idea is it's not evolution, it's not a geometric flow, it's an evolution flow, but it allows to construct that is on dimension 6 with one parametric family of a diffuse structure. Here, rho hat is just a J of the rho, so the idea is rho plus R is rho hat, which are the 3-0-4 that you have. And if the family satisfies that equation that I wrote, and you start with an R flat condition that we mentioned before, then you have a family of R flat as a structure, and you have a natural way to construct a parallel on the product of n6 times r, some interval. That's the reason why you don't get a complete magic. But there is a strict relation between dimension 6 and dimension 7. Using that, Hitchin, in fact, Robert Bryan showed that if you have a 6 manifold with a non-flat symmetry structure, which is really analytic, then you can embed in a manifold with parallel structure. We know also that the hypersurface, oriented hypersurfaces inside the manifold, a 7 manifold with parallel structure, have such type of symmetry. Let's go now to the complex example with holonomy G2. This was a difficult task, and the first thing that one can remark is you have a strong restriction on the topology in this case. If you take an compact with a parallel G2 structure, then to have holonomy G2 corresponds to a finite coordinate group. The first example we're constructing by Joyce, essentially using orbital solutions together with a two-button method. So essentially the construction is starting with the T7, the 7-dimensional torus. You take a finite group, you portion by a finite group, which is contained in the authority of the usual track method. And what you want to have, you have an orbital here. You start with the orbital. Of course, you need some condition on the orbital. If I will go back to this construction later, because we adapt this construction, in the case that the G2 structure is not anymore parallel, and then you look at the family of free form, which do not use directly parallel G2 structure, but are only closed. So, and then you use the perturbative method to the form. There are other constructions that use gluing. The first one is due to Alexei Koparev, using gluing and free form, which are Fino, which was generalized later by Kotti, Askin, Ostrom, Chi. And more recently, there is a nice construction by Joyce and Arjan, where they essentially they glue a family of Gucci Hanson spaces, which are parameterized by a non-vanishing harmonic one form. I will go back to this because this construction will be also generalized in the context of closed G2 structure. So the general idea, roughly speaking, is always to start with linear condition, if is 0, and then try to solve in some way the non-linear. Okay. But you always start with a family of closed G2 structure. Okay, let's see the definition of closed G2 structure. The definition is quite natural. You impose that the free form is closed. Then automatically, if you look what you compute the differential of star the free form, you have only one term that is going on. You have something like tau HP, and this tau, which is the only left portion that you have, has some nice property. In general, you have the space of two forms respect to the action will be two. You have two irreducible components. And one of the reducible components is the one that works to the reaction. And you can see from there that you have the property that star of tau is just minus tau HP, and tau, if you do the wedge of tau, is star P. That's a nice thing because what is saying that condition? He's saying that in particular, tau is just this star P. So if you take the differential of such tau, it's just the Laplacian. So from here, you can see that the Laplacian is exact. It's just a differential tau. Another thing that is important is to define a calibration on M. So for any tangent-oriented plane point, the restriction is just one due to Hartmann-Lassel. And since you have a calibration, you can define a positive form, which are just calibrating. by the free form. And here, in a paper on Robert, we study in general what you can say about the magic property, so about the rich tensor and the scalar curvature. And what turned out, the scalar curvature is always there. Okay? So that means that on common manifold, we don't have many sections. That's the first thing. Okay, one can try with symmetry. What happens if you impose symmetry? Generally starts on the existence of closed G2 structure on complementary manifold and no. Okay, when it takes that these, I mean manifold which do not admit any part of G2 structure. One can look for the automorphic group. So take the group of the homomorphic preserved in a free form. When it's compact, you can work on the Lie algebra. The Lie algebra is just a vector field. For which preserve free, then derivative with respect to x of P0. If M is compact parallel G2 structure, you don't have anything, right? The automorphic just parallel. It's just zero, the zero, the algebra, the level of the algebra. So what we can say when you have a closed G2 structure in tau is nothing. We have a result for the sign of error that gives a restriction. In fact, this is easy to show because the two form the contraction by P XP. And this is what, because the star is just the form itself times P, and everything is good. And that's very strong because in some sense, it puts some restriction on the automorphic group. And we say in particular that the automorphic group has to be a dimension less than equal. That means that on compact homogeneous space, you cannot have such structure. And also for homogeneity one, you have a restriction. The only case is a case with so with this type of symmetry, imposing that you have a transitivity group preserving the free form, you don't go far. But fortunately, there are examples. You have to make weaker your assumption on the symmetry. And the first known example, these are all locally homogeneous examples. And the first example was constructed by Marisa Fernandez, is the main manifold, is the compact portion of Fibonacci important by them. So one of the problems is to see, okay, how many examples, what happened in this case? Everything can be detected at the level of the algebra here for invariant to the structure, and I just mean a structure induced by some structure at the level of the algebra. Of course, one simple remark due to Miller is that you have a restriction on your Lie algebra because the Lie algebra has to be model. That is the condition to have the comma function. Here, I will be very clear on that, but I just want to give an overview of what is known at the level of the algebra. With Fino, we show that this is completely a different picture of simplicity. The closest structure has some analogy with simplicity form, because again, you have a form which is closed and non-degenerate. But the picture is completely different for G2 structure. With Alberto Fino, we describe what are the non-solvable of the algebra, and it turns out that if you look for the line recognition, you have a strong restriction because the same sequence part is always SM2R, and then you have also a restriction on the right. One thing that it turns out that if you have no trivial center in your Lie algebra, unimodular, then the Lie algebra is to be closed. In such case, so when you have a tolerable Lie algebra and no trivial center, we can describe completely the picture of what is going on. The important case was solved by Diego Conti and Marisa Fernandez, and the non-important case was solved by myself with my former students, Raffero and Salvatore. Okay, now let's go back to the topology. one of the problems that is completely open for manifold with parallel teaching structure if they are formal or not in the sense of rational homology. We know by a paper by Mann a time ago that if you take the typical Joyce example, so the example found explicitly by Joyce of sectional holonomy G2, these are all four. Okay? But if you don't know in the if this is general, all the examples until now we will check have this property. Okay. An important tool that we use also is resolved by Marisa Fernandez and Munoz that reduce to study the formality of the manifold in terms of formality involving generator essentially of the model of degree, not all the degrees, but the degree up to n-1. So what that means? That if you want to check if the third manifold is formal, it's enough to check the free formality. And that's a lot in the computation. So the problem that look, okay, here it would be 1 and 1, first basic number, because in fact, we still have hope to find P1 equal to 0. This is a completely open problem. So it's not clear if you can have an example of how a manifold with P1 equal to 0, first number equal to 0, and then we enclose it. No problem. We produce an example. The P1 is 1, which is the formal. So the formality is saying that it doesn't distinguish the condition to have a closed structure. The mean manifold, the example that they were know before, they were all known for. And essentially, we construct that example of applying the joint technique in a different situation, starting instead of the totals, considering an inlet. As I say, there are no examples in the case B1, 0. And for instance, this is looks a simple example if you write, but very difficult to understand if the cell sphere has not closed structure open, and there was that to be later also, because there is another case where we don't know if you have an example or not, and it's a case when we create or complicate. So no example out of the law. So it seems that there are restrictions on the topology, but nobody knows why. Or maybe there are not. Okay, what is the motivation to construct such example? Here represents one example, but one can generalize to other examples. The problem that unfortunately, I will explain it is the problem at some point. So instead of looking for, sorry, I was covering all the time with instead of starting with the 7 towers, like in the joint picture, we start with an in manifold. Especially, what was it?
The laptop needs.
The laptop. I also destroyed the laptop. Thank you. So they put to there.
Yeah, don't worry.
I go. Okay, so here we consider this case where the new Poisson group is a free set. In fact, you can use other cases. Unfortunately, all the cases that we use, we always go back to V1 equal to 1. There is a case where we were very happy because we go to V1 0 at the level of our control, but then we are not able to solve the singularity. It's very complicated. I don't know how to solve the singularity in that case. So we have a non-equal without property, but we are not able to solve the singularity. I will not describe the group, I just say few things one can describe. The group is the group of the matrices, so that's 4. But the essential thing that n is a copy of R7. So you have a global coordinate, x1, x7, and you can write a basic one form, a global frame in terms of such coordinates. Good. We have a natural Latin. In this case, you just take a copy of x1 essentially given integer, and then the other coordinate just give a copy of theta 6. And then you have a natural invariant clause T24. A nice property of this manifold, and we will use that for many things, is that the Nernst manifold can be described also as a manifold of 6 torus by diffeomorphism, which is induced by element, essentially. And so the manifold projects over S1, essentially, and we will use later this projection. Now we need to find an action, and the action, okay, at the end, the type of singularity that we will have will have something like T2 over theta 2 times T2. Okay, so we need to split like 4 plus 3, and that's the idea. So you change the coordinate of x1 is 2, x5 is 6. And this law is good, it's preserving the length, it's going to the quotient. And you get an orbifold. We show that the first thing we show that the B1, the first vector number of the orbifold, is 1, and that's an induced clause G24 orbifold, of course, because we are working terms of orbifold. And to compute the cohomology is very simple in some sense, because we know by the theorem how is the cohomology of the Nernst manifold, and you just look for the theta 2 invariant form. So you easily find the cohomology. Okay, the difficult part here is to find the smooth resolution to resolve the. Of course, one can see, okay, this is similar to joint state. It's not quite similar. We use the same technique, but it's a bit different. Why? Because in joint case, you use E7. Okay, so you use the flat case. Here we found the Nernst angle, which is not the flat case. So we need to adapt the conception. What we can say about the singular locus? If we take the projection from M to the orbifold, then the singular set of the orbifold is just the image under such projection that fixed point up. And we have extension that S consists of 3-dimensional space that you could describe in that picture. Okay, I put in blue the element A1, A2, A5, A6 that correspond to the previous action before. And the important thing is that the S prime A are included in the pre-image under the figuration of S1 of that element. That means essentially that are abelian and has to be copy of T3 of Fino. So the singular locus is just a union, disjunct union of 16 copies of the free torus. And we know that the neighborhood of each component of the singular locus is isomorphic to the product of T3, T2, times the open hole over the cosmic theta 2. And then we replace that with an appropriate neighborhood of the Guccian space. Here is where we apply a similar thing like in the case of Joyce's apple, but we need to modify gluing. So the glue is completely different. And we show that we have our resolution. So we get an example which do not admit, also we show that doesn't admit an hierarchy structure. The fundamental group is not changing when we take the resolution, and it's equal. Here can adapt to the construction of Kanjani and Joy to construct with that technique. An example, again, will be 1 equal to 1 and non-formal, but again, B1 equal to 1. We also studied the associative free form of such manifold. I will go back to this example later when we see the Hitchin volume function, because this example is a special behavior to expect that. Anyway, another thing that one can easily describe here is to describe the associative free form example. This is we apply a result by due to Joyce. If you have a seven manifold with a closed G2 form and you have an involution which preserves the free form, then the fixed point set is an embedded associative free form. So it's calibrated by the free form. If you start with compa, then you get compa, and then we use a specific involution. The nice thing about this involution that if you take the fixed point set, this is again the joint union, this time of a copy of the free torus, which do not intersect the singular law. Using that, we can show that our sample has 8 associative free torus inside, and we can also construct a three-dimensional family of non-trivial associative information. We have also regard about co-associative manifold, but I will not describe. I want to go to Laplacian flow. Okay, the idea, this flow was introduced by Robert, and it was inspired, in fact, by a work by Nigel, and the work that I mentioned at the beginning that is related to the volume functional, because it appears that the gradient flow associated with such volume function. Now, let's give the definition of the flow. So the original idea is to use a geometric flow to the form closed G2 structure, and eventually obtain a parallel one. Some cases obtain, other cases no. And there are still many problems, open problems related to this flow. So the idea is that you start with a closed G2 structure on 7 manifold. The Laplacian flow is an evolution. So you evolve with a family of G2 forms, let's say, and they evolve using the Laplacian. So remember, the Laplacian of PT is an exact form. So it's the differential of tau P. How torsion, you impose also with the form of closed. And what happens, you can see that since you are evolving along exact form, the form, the solution of your flow belongs to the running class of the region before, the surface before. If you look how we evolve the matrix, you can see that it evolves closely to the Ricci flow, to the usual Ricci flow, but you have an extra term, which is involved with it. If the manifold is compact, then the stationary point is the flow are just a parallel structure. And this is a very nice feature about this Laplacian flow, because this is the natural flow, the gradient flow of the Hitchin volume function. Let's say essentially you take a free form in the class, in the ground class of Fino, which is non-degenerate, and you just take the volume. So you take the insular over it and the keyword stuff. That's volume functional, the property to be monotonically increasing along the flow, and its critical point at parallel G2 structure. And they have also strict local critical point. I want to point out this thing that what's an open question by Robert to see if this volume can be bounded by a both. And the example that I presented before, that was shown recently by a student of Alex, that that functional is unbounded in that case. So that's means for me, you don't have that. But for that case, you have such, let's say, strange situation, so it's not clear. It's still mysterious, let's say, this volume function. We have a short time resistor. This is was proved by Bayer, using the chart 3 plus Marsh-Moser theorem. Okay, I don't want to talk about results, general results about the flow, but I want to see what are the solutions. No, there are solutions, pretty solution on the group. On 47, for the $7 with homogeneity 1, this is a nice result because it's saying some sort of convergence. The convergence is to the flat method on 27, essentially. We look a bit. I look with a Fino, also Hotter, proves something. What happens if you go to lower dimensional reduction? So if you connect in dimension 6 what is going on, or in dimension 4. And the nice result is in dimension 4 also, because this is a result by Fine Yao, where they show they start with a special type of closed GT structure. It's on the product of a 4-manifold times T3, and phi is essentially induced, is the natural one, and it is used by hypersymplectic structure, which is the definition which is honorable, and it's not clear if you can have some 4-manifold which have hypersymplectic structure and no hypercarrier structure. There is an open conjecture about that. Lambert and Lotai has also, more recently, a long time existed the convergence of the Laplacian flow in cases this time which are related to co-associative fibrillation. And these are something like fibrillation of the fiber is before, and the base is simply connected open in our fluid. But again, we have a special picture, let's say, as for the flow, some information you can have when you have self-similar solution. What that means self-similar solution, it means that the solution is of that form, sigma t is a non-zero scalar function, and then you pull back using a family of differomorphism. What happens in this case, you can figure out what is the condition to be self-similar, and the condition is that the Laplacian is a multiple of phi, so it's lambda phi, plus the little with respect to some vector. So like in the usual Ricci flow picture, you distinguish a type of solid with lambda. If lambda is negative, you have a shrinking solitone, lambda 0 steady, and lambda positive expand. But we have a completely different picture from Ricci flow, because, okay, we have a restriction. This was proved independently by Lee and Lothar by on a couple manifold and in Laplacian solitone, which is not final, must have lambda positive. So what does it mean? It means that the Riemannian only expands, but no example of couple manifold is known with such expansion. So it's not clear you can have such expansion. The only state are parallel, and so then this is the open question. If you remove the assumption compact about the compartments in the non-compact case, you can have everything. Homogeneous, not homogeneous, all the time is not the problem. You can also have inhomogeneous examples, which are gradient solitone. This is the construction by Ball and Fodder. The construction by Ball is quite nice because we look not only, we'll see later, look at special type, in fact, of closed structure, which is related to the Ricci flow. Of course, there's the main problem that we don't know if the flow develops finite type singularity. This is completely open. One doesn't know. Very recently, asking and Knoxville construct continuous family or local homogeneity one gradient Laplacian solitone with such symmetry SP2 and SP2. And they construct a split example on the space of artisan 4 on its 4. And it was not known never not homogeneous. Very recently with Alberto, we construct a homogeneous gradient Hitchin function. This is the first example of a gradient solved for a geometric flow. And it was not clear what, but that's I only put the group. The group is very simple to describe and give a homogeneous steady. And also it's the first example in the terms of geometric flow, or one, what is called one extension. And the function that gives the value is just extend. It's the coordinate. It's up. What exactly is important? When you are expanding the Laplacian polynomial, if you look at the condition, lambda p, lambda is positive, so lambda p will be exact because you will have a term in the tau and the term in the linearity, which is again exact. So this form, the free form to be exact. Nothing is known in general, there is some restrictions. And of course, what we look is, of course, it's natural, right? Many examples are of that type, like proportion of any group by lattice. So we look with Lucia Martin and Alberto what you can say about compact portions of that type which invite the subject form. And it turns out that you can have. So it's very strong restriction. The proof is done in non-solvable case and solvable case. Unfortunately, we do not have a proof that put together the two cases. It would be nice to have because maybe give a general picture of what is going on. I don't know much time. I am so mostly. We have 20 minutes. Oh, I need to talk. We distinguish. I was very quick. We distinguish this case in non-solvable case and in solvable case. In non-solvable case, essentially, we show directly that we use that in fact this case is quite tricky. You have 4 isomorphic classes. And for free, one doesn't have any exact Hitchin structure. And for the other one, we show algebraically that the group, the corresponding group, cannot have any length. So that's the way I will show. The solvable case is again using a reduction to dimension space. Because this is the result due to theorem. They show that if you have an algebra with a closed Hitchin structure, then you always have a codimension 1 modular ideal. So using the magic associated to the free form, to the Hitchin structure, you can decompose your algebra into pieces, X and the orthogonal complement. And one can write, that's the main thing here, that you can describe your algebra as a semi-direct product of a copy of R that corresponds essentially to the orthogonal complemented time for some derivation. And then you can write down also how is the free form, because the free form will be just, you have induced a free structure on your F, essentially. And you write down your free form like omega, which is the two forms defined in the free structure, which the dual metric of a unit vector on the orthogonal complement plus rho, which is the other free form. And then we impose, and that turned out to be a strong condition that the free form is to be exact, but this is not enough. I mean, in the solvable case, unimodularity doesn't, okay, we know that it's a restriction in general to have compact portions by lattice, but in the solvable case, this is defined treated by Gala and Anna, where we consider other stuff. But in the time, which is the condition for a algebra to be strongly unimodular, which turned out to be more strong than unimodular, implies unimodular, And the condition is the following. Let's start with your radical G. Let's take the mean radical. Let's take the descending central series. And the condition is that the trace of that is equal to any quotient Ni over the next ideal in the central series at the That's I'd also point out that with the modular integral, you can show that there are subforms which are close, exact, to form a unimodular. So unimodular cannot be. It would be nice to have to figure out better why this is going on. These are the only negative, in fact, the results. I mean, there are no examples like that. Or maybe it's related to the other question, if you are expanding. So it's again related to that. Okay, let's go to the last part. This is the part related to a Hitchin condition on the Hitchin tensor. Was shown independently by Clayton, Ivanov, and Robert Berger that if you take a compound manifold with a closed structure, then okay, one can look for the alpha. What you can say? What happens if the match is alpha? Then they show in a different proof that the torsion is to be so recently, Pine, I think it showed that you can prove the same result removing the function compactness and only imposing that the matrix is complete. So remind the question, the non-complete case, what happened? It turns out, and that's the way how Robert Berger proved the result, that there is inequality involving the integral or the square of the scalar curvature with the integral of the norm of the Hitchin tensor. You have that inequality in general, and you have an equality which don't leave. You have this condition on the differential of the torsion. You see here that the condition is quadratic. It's quadratic on tau. You have a condition on the norm of tau squared, and also on the star, tau h tau. This is what generalized by Gary Ford as quadratic Hitchin structure, because you can change one of these coefficients, the lambda, the parameter lambda, and it turns out that for lambda, such value you have alpha, for another value you have this condition, that equality, that the only cases disappear. And this is what's called by other guys extremely rich pitch, because essentially you have that equality for involving the rich tensor and the scalar curvature. We Alberto Rafael will study what is going on. That's another question. What happens if you start with extremely rich pitch structure and you evolve under the Laplacian flow? We show that the solution remains extremely rich pitch. That's another difference from usual rich flow. Okay, one can ask, this condition on the rich is quite strong, right? What are the examples? The first example was constructed by Robert Berger. There is an example on compound non-homogeneous space. This is due to an from Jorge Loret. And is a solvable, is a quotient of the solvable group. And we show with Alberto Rafael that this is the only case that you can get, only unimodular group, which admits such left invariant extremely rich pinch. What we can say about solitone, if you work at the level of the group, and you have this extremely rich pinch condition, that always implies steady solitone, but the converse is not true. So you have one direction, but not the other direction. We show that you can have a solvable group, which has a steady Laplacian solitone, which is not in the GP. So summarize, we have some design, the gradient stuff now is called, but there are many questions open, coming back. There are questions, there are no structure, topological structure, you can see from the example. So the old example have been one, at least one, and the three are positive. The question about the substance is strictly related to the solid condition. And again, for Laplacian, the main problem that one doesn't know which you can develop, as you say, final path singularities, and also the volume, the picture about the volume is not clear. I mean, we know the discussion is fine at that, but the examples are showing different behavior. Anytime that you look, the value function, you will find different behavior. I think I finish here. Thank you very much for that.